Given an object with an emissivity of 0.800, that's clearly at 3 significant figures there, a surface area of 37.5 centimeters squared, and a temperature of 15 degrees Celsius, what is the total radiated energy output of this object given that the Stefan-Boltzmann constant is equal to 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth? That's probably one of the most novel sets of units right there we've seen in a while. So the radiation law that we're going to use for this naturally is a Stefan-Boltzmann power law that we've been talking about. And so I'm going to write it down here. And so to answer a question like this, there's maybe a number of things we need to do. I mean, we're basically given all the numbers we need to put into this, but not everything is maybe just ready to just plug it in, because there are some units issues here. Maybe starting with area was given to us as 37.5 centimeters squared. So is that 0.375 meters squared? Just move the decimal place twice. And I'll pause dramatically for a second there to say, no, that's not going to be correct, because this is area, right? We actually need to convert centimeters to meter like twice. And so that would mean you'd have to like really divide by 100 twofold, right? Like divide by 100 and then divide by 100 again, which would really mean I'd want to move this decimal place 2 more times. So let me see, how can I do that? I'll first, I don't know if actually, you know what, this is not going to work. Scratch that. I'm just going to erase it. I think I left enough space here. It should be 0.00375 meters squared. So, okay, we've taken care of that. The next thing is E. That one is easy because that's just a pure number. So that's that 0.8. I don't think I need the extra 2 zeros there because they're not really placeholders. They're just reminding me or telling me where I'm going to wind up rounding when I finish this. Then we can multiply by the Stefan-Boltzmann constant, so that is given to us as well as 5.67 times 10 to the minus 8, and that's a lot of units to squeeze in here. Let me see if I can do it. That's one of the pitfalls of writing all the units. You need to have plenty of space, which is why sometimes I skip it if I'm running out of space, but I think I can do it here. And then for the 15 degrees Celsius, I need to remind myself this needs to be in Kelvin. The Stefan-Boltzmann law, you know, maybe kind of like the ideal gas law, is based on physical temperature relative to absolute zero. So I shouldn't put in 15. I should add 273.15, which I think is then 288.15 Kelvin is actually the correct value for the variable T, or the symbol T representing the temperature in Kelvin, and then that will be raised to the fourth power. So now I have enough information there to put all the numbers from that expression into my calculator. My calculator says 1.172678085 in case you want to compare an exact answer to what I had, but I think I can round off right there. Let's check out the units. This is supposed to be a power, right? Power is usually in watts, so I think I'm going to expect watts to come out of this. And that kind of explains why there was these crazy powers of units here, because I need the Kelvin to the fourth to cancel a temperature raised to the fourth power. I need meters squared to cancel against the area that was given there. So that leaves the watts that I'm expecting. So I think that'll be the answer, and it looks like it checks out.